everybody. Welcome to our next session at Czech's London conference. I'm happy to introduce Daniel Lebrero to you. Hi, Daniel. Daniel will talk about Clojure, but it's not a Clojure talk. It's about a Clojure mindset. So very interesting topic. What can Java developers learn from a functional paradigm, which is so central in Clojure? Okay. So for all you out there, please use the chat and the question tool in Swapcard to ask your questions, and Daniel is happy to answer them in the end of his session. And with that, we should start your session. Please feel free.
Thank you very much. I'm going to start by sharing my screen. Let me see. Sure. Oops. Can everybody see that? Are we good? Okay, thanks everybody for attending this session. My name is Dan. I work for Akvo, and we are here today to talk about Java, but with a Clojure mindset. I want to start with a quiz, and you can type it in the chat. Who can guess what is that? So if you want to type it in the chat, I'll wait 10, 15 seconds to see who can guess it. I don't see anything in the chat. I don't know if it doesn't work, but that's basically what Clojure looks like the very first time that you see it. Yeah? And I want to point three important things on that picture. The first one is that it's very ugly, right? Some people will say that it's even disgusting. The second thing is that there are some things that make no sense at all on that picture. For example, why would you want to have a bag in your mouth? And what the hell is that? And what is it doing there? But last, the most important thing, it's that it's alien. And maybe when we are looking at this picture, we're actually looking at it from our human point of view, from our Java perspective. So maybe we are not being fair. And with a little bit of time and the help of the Hypnotoad, maybe that picture will look more like this. Because with understanding, it will come a change on our point of view, right? I know what you're thinking, right? It's like, well, you know, Wonder Woman is not technically an alien. And if we are talking about Clojure, probably, you know, the picture should be more like this with a ton of parentheses. But still, if we spend some time trying to understand Clojure, maybe we can learn some superpowers that we can use in our day-to-day job as Java developers. So for those that are not familiar with Clojure, Clojure is a functional, hosted, dynamically and strongly typed list for the JVM. So what we are going to do in this session is using a real world application as an example, see how Clojure changed the way that we design and we build that particular application. For a little bit more context, when I got involved in building this application, I have already been working in Java for around 12 years. And I have been working with Clojure around 3 years. So I will consider myself to be on the stage 2, weakest stage 2 on my transformation to a full-blown failure. And the application that we are going to be talking about is one of these bonus systems that you see in some betting industries. One of those that you see that if you place a deposit, you will get double the amount cash for free, or if you create an account, you will get 10,000 euros for free. Obviously, nobody's going to give you anything for free. So if you read the terms and conditions, to be able to withdraw that free money, to be able to put it in your pocket, you need to place a bunch of bets or do some activities in the system. Also, I don't know if this is common in other bonus systems, but in our case, the user had a limited amount of time to actually place that bet. So removing all this marketing fluff, what our system had to do is to give the client some money if he has placed loads and loads of bets, and he has done that within a limited amount of time. From an implementation point of view, what our system needs to do is needs to keep track of which bonus are available, which clients have signed up for each of the bonus, And then it needs to keep track of those activities that the user is doing in the system. And these activities in our case were mostly deposits and bets. So let's start with the first big difference between Clojure and Java. Clojure is a functional program language, and Java is an object-oriented. Of all the principles and practices and techniques that are usually associated with functional programming, I want to focus on one that in my personal experience had made the biggest impact on the way that I build applications. And I think it's especially important because it can be easily translated to any programming language. And that's the concept of a pure function. Yeah? Pure function is a piece of code that always, for the same input parameters, it will return the same result. So always same input, same output. And why are pure functions so important? Pure functions are easier to understand. Yeah, because to understand a piece of code, you just need to keep in your mind the input parameters that that function has. Pure functions are a little bit like physics laws, because once you understand how the physics law works, you can rely on it working exactly the same time every single time. Yeah, and because pure functions are easier to understand, they also mean that they are easier to change. And change is what we developers do for a living. And we rarely write any new piece of code that is completely new. We are usually just modifying a system. Even if you created your new project like 50 minutes ago, you are already in the business of changing that new application. Now we're talking about pure functions. We need to talk about its evil twin, side effects. So side effects are those things that make your code really complex, and it makes your application messy. Because now to understand that little piece of code, it's not only enough to look at the code and the input parameters, you have to take into account all the dependencies of that code and all the libraries that it's using and all the possible states on the database and all the possible states of the network. And you have to think about what could happen if several threads were running that code at the same time. So the context that you need to keep in your head to understand a function with side effects, it's just huge. Once you have side effects in your code, you don't really know what's going to happen the next time that you run a piece of code. And this happens to us all the time. So one of the key insights on my learning about functional programming is that side effects are the enemy. And most of the concepts and techniques that you find in functional programming, they are all about fighting and controlling these side effects. There are basically two types of side effects. Side effects that change the state of your application, and then you have IO side effects. Of the IO side effect, we can distinguish between input side effects, also known as co-effects, and output side effects that we'll just call effects. So what we are going to do right now is we're going to look at how we can fight each of these three types of side effects. And we are going to start with the state. In the case of our bonus application, the bonus application needs to keep track of the client, which clients have signed up to which bonus, and it needs to keep track of the activities of that client through the system. To do that, you can imagine that we keep a hash map where the key is the client ID, and then we keep some kind of client bonus object. This object will have a reference to the client and to the bonus, and it needs to keep a list of all the deposits made by that client. And this deposit list would have a bunch of deposits, and something similar with the bet list. So this is basically the object graph that we are going to work with. And we will have one of these for each of the clients. Now I will traditionally, what I would have done for the state management is I will make every object responsible for their own state. Okay? So basically this means that every object, for example, the hash map, will get like a little machinery to make sure that the several threads we're trying to access or modify the internal state. At the same time, that little machinery will take care of making sure that the threads will see a consistent state. Yeah, and in the similar fashion, the client bonus will get its own little machinery to make sure that several threads accessing it will see a consistent state. And I will do that basically for each and every object. Now, what does it mean, each of these little machineries from a complexity point of view? It means that whenever you go and have to change the code, not only you have to think about the business logic that you are trying to implement, you also have to think about the concurrency and the multi-threading and the timing issues that can happen when multiple threads run that code. So you are mixing in the same place rules about your business and rules about concurrency. One of the things that I learned with Clojure is that to simplify your code, what you actually want to do is separate these two concerns. On one hand, you want to write your business logic, and on the other hand, you want to do your state management. So how we go about this? First thing that you do is that you make everything immutable, even that hash map that contains all the client bonuses. Now that everything is immutable, when you write your business logic, you don't need to worry about all the threads messing around with your logic. For the state management part, what Clojure gives you, it's a construct or a class called an atom, which is more or less the same as a Java's atomic reference. So let's see how it works. An atom contains a reference to that full immutable state, right? And it contains some machinery to be able to move from one state to the next state in an atomic, consistent, and isolated way. To understand really how it works, let's see what happens if two threads at the same time try to modify that reference in the atom. So let's say that we have two threads, thread 1 and 2. And the first thing that we will need to do is they're going to calculate the new state of the application given the current state of the application. Let's say that thread number 1 finishes before thread number 2. Yeah, and thread number 1, the new version, the new state of the application is that current state. Now that he has finished, what it will go to the atom, and using a compare and swap operation, it will check that the value that he used to calculate the green value is still the white value. And in this case, because the state contained or pointed reference by the atom is still the white value, it means that the atom will point to the new green value. When thread number 2 finishes, let's say that it calculates a blue value, it will go, I will try to do again a compare and swap operation. Because this compare and swap operation, it will fail because it used the white value to calculate the blue value. But right now, the atom has that green value. So what it will happen is that thread number 2 will need to start again all the calculations, but this time with the current valid state of the atom. So in this case, it will calculate the red value and the atom will move time. Yeah. Now, you as a developer, the only thing that you need to care about is given the current immutable state, you need to write a function to generate the new state. And that atom machinery takes care of detecting all the conflicts and rerunning the function if it needs to be rerun. So from your point of view, you just need to do that function from one state to the next. That's your business logic. Now, to make sure that we are in the same page, I want to point to two things that I think are important. First thing is that the valid states of your application during that time were the white, green, and red states. Nobody ever saw that blue state. That didn't exist, basically. The second thing that I think is important is that if a thread at the beginning of time, and that's time 0, it gets hold or it reads the current state of the atom as the atom moves in time, that thread number 3 still holds a reference to the original white value, which means that that thread 3 can be working with some state value. Yeah. Now you may be wondering, well, if every time that I want to change the state, I need to generate a whole new object graph. You know, this immutability thing is just going to be extremely slow, right? The performance is going to be crap. And it's true that immutability comes with a performance cost, but it's not as big as we expect. Let's say that you have this white value, and now you want to generate that green value. And that green value, the only thing that you really need to change is one field on that bed class. Yeah? So that you will need to create a new bed object. Now, because that bed object is being contained within a bed list, it means that you need to also create a new bed list. Now that bed list, again, is contained by the client bonus, and the client bonus is being referenced by that bucket on the hash map. So it means that to create or generate the new green state, you actually just need to recreate those 4 objects, because you can reuse the rest of the white values because they are immutable. And we know that sharing immutable objects it's cheap, right? This is a technique that in functional programming is called structural sharing, which makes immutability fast enough for a lot of applications. Yeah. Now, again, this is still slow, but you save a lot of coding time and a lot of concurrency bugs. In fact, how many of you have to ask this question every day, right? Is this thread safe? Now, with immutability and atoms, you still need to ask this question, but to answer it, the rules to answer it, they're a lot simpler because they don't involve knowing about the Java memory model and the happens before semantics. The rules are the following. The first rule is that state is always consistent. If you read from an atom, you never ever see a half-baked value because everything is immutable. The second rule is that the function that you use to move from one state to the next, it must be a pure function, because as we saw with thread number 2, the function can be rerun several times, right? So that function cannot have any nasty side effect. And the third rule is that this mechanism about atoms and about moving from one state to the other is just safe within that pure function. Anything that happens outside the pure function can still be subject to race conditions. So how this affected our Java classes? So the first obvious thing is that everything, all of our domain objects were immutable, including that, for example, that list of deposits that will be mutable, and we'll need to create a new one if we wanted to modify it. Now, for the state management part, instead of using an atom and having that map with all the clients in one single atom, in our case, for our business logic, what one client does doesn't affect the outcome of another client bonus, which means that for our business logic, we just need to make sure that the client bonus, just the client bonus, it's seen in a consistent state. So what we did is just create one little machinery for each of the clients, one of these atom-like little machineries for each of our client bonuses. Now that machinery is actually provided by the compute family of methods on the concurrent hash map. And so that's compute to take care of all this, detecting if there is a conflict and running your function if it detects a conflict. So we put all of this together. This is how basically the class that holds the state will look like. We'll have a concurrent hash map, and then whenever we get a new event, we'll ask the concurrent hash map to advance state. And if you see there, we decided that the best place to calculate the new state it's the client bonus itself. Yeah, so that next state on the client bonus, it doesn't modify the client bonus itself, but it creates a new instance with the new version of the client bonus. Yeah, so this is how we will deal with that side effect that modifies state. Our next side effect, let's look at effects themselves. Yeah? Effects are things that your application needs to do in the external world, to, for example, in our case, send a notification about the progress of the bonus or pay the price. Traditionally, what I have always done is write some kind of service class that will take care of the coordination of different parts of the application. Now, if you look really about what that class usually does, the code that it has, it usually takes care of two things. On one hand, it decides which side effects it needs to execute. And in the other hand, it executes the side effects themselves. And it deals with all those messy details about errors, error handling, and all that kind of stuff. So that class is actually doing two things. So if we want to follow a more functional approach, what we want to do is separate those two concepts. On one hand, we want to decide which side effect should be executed. And on the other hand, we want to execute those side effects and deal with all the messy details of the real world. To do that, what we decide is that that client bonus, when we calculate the next state, not only we calculate the next state, but we also calculate the effects that should be performed as part of that transition from one state to the other. Okay? This has the benefit that your effects things that your application needs to do, they become first-class citizens, right? And that still, that next function, it's still a pure function. It doesn't execute any of the effects. It just decides which effects should be performed. So for example, in our case, this will be one of those effects that need to be executed. Notify the client about the progress. Now, even if it's the pure business logic, the one that is calculating these effects, things like error handling or how those effects should be executed, that still can be decided by the pure logic. For example, we could wrap this effect into an ignore error policy, so that if there are any errors when executing that effect, we will just ignore the error. And this is something that we can do in the business logic. The business logic will take care of deciding which effects, which error policy they need to handle, right? In this case, maybe in other cases, we can decide that the correct error handling policy is to stop the JVM. In a similar fashion, if the pure business logic can decide, for example, if the effects should be executed sequentially, so that if effect number 1 fails to be executed, it means that effect 2 and 3 will not be executed. Or if the effects that we want to execute, we can execute them in parallel. Yeah? So executing effect number 1 should not, affect at all effect number 2. And it also means that we can run effects in parallel. Now for our bonus system, because we had a very limited amount of effects, instead of building all this generic effect system, what we decide is to create a very rigid, a very strict way of defining those chains of effects. And we actually use the Java type system to encode in the type system what were the valid chains of effects. Okay. Now with this, our pure logic, it's still, it just calculates which effects need to be produced, returning some structure like this one, but we still need to execute the effects themselves. And in our case, what we decided to do is to ask the effects to run themselves. They had the most knowledge about how to run themselves. And now this is how the interface of an effect will look like. And if you see there, what we are going to do is pass that all dependencies object that contains all the HTTP client, EMS clients, repositories, everything that you could need to perform a side effect. Now, this has the benefit that it's very obvious which part of your code base are pure functions and which part of the code base have side effects. Because to be able to perform any side effects, you need to declare that all dependencies as part of your method signature. Now, this sometimes a little bit annoying because it means that you need to pass that all over the place sometimes. And also that all dependencies object is a little bit ugly because that basically, it's like 90% of your Java Spring context. It will have, have there everything. So we put everything together. This is how the code will look like. We ask the state holder to calculate the next state and the effects that need to be produced. And then we just ask the effects to run themselves. Now, question, is this thread safe? Does anybody, well, I think the answer is obvious. I wouldn't be asking the question. So if we look at the rules that we said about atoms, one of the rules is that anything that happens outside that atom machinery, it can be subject to race conditions. And where is the race condition here? They say that we have two threads that they want to modify the same client state. They have to do something in the client, right? In the same one. So that atom machinery will make sure that both threads are making an atomic, consistent, and isolated decision. So far, we are so good, right? The state is the correct state, and the effects calculated that they're correct ones. Now, what can happen is that thread number 2, it starts to execute their effects before thread number 1 had time to execute their effects. And this, depending on your business logic, it can be valid or invalid. So it depends on the domain. If it's not valid for your business logic, what Clojure provides, it's something called an agent. You can think of an agent as an atom. It has the same kind of machinery, but it has the extra guarantee that it's single-threaded. So if you're familiar with Erlang or Scala actors, it provides more or less the same concurrency model. Now, in our case, this kind of race condition was not valid, but we still decided not to use agents, and we still use add-on. And why was that? Because we were planning to deploy this application in several instances. And now that we're running it in several instances, now we are in the business of distributed system programming. As the side effects that we need to produce, there were no way to make them in an atomic way. The distributed system programming theory tells you that you have to choose between at least once or at most one semantics. So what we did is for each of the effects that we had in our application, we decided if we are happy with at least once or at most one semantics. For those effects that they have at least one semantics, we just didn't do anything, any coordination. All the instances will, run those effects. Now, for the effects that we wanted to have at most once, like for example, paying, what we will do is we use some kind of coordination mechanism to make sure that just one of the instances will execute that effect. Now, in our case, we decided to use just a plain old relational database, so that if there is, for example, a race between 3 instances to pay that price, the database will make sure that only one of them gets the go ahead and the other ones will do nothing. Now, you just want to point out that it was still our pure business logic, the one that will decide if some effects, if we want them to be at least once or at most one semantic. So this was all part of the pure business logic. Now, by following this, co-effects. So this is the last type of side effect. So co-effects is basically the input data, the data that you need to make the decisions on your system. Okay? So again, in our case, for the bonus system, we need to keep track of which clients have signed for which bonus, which deposits, and which bets they have made. And we also needed to know what time it was, because the user had a limited amount of time to perform all those actions. As I have hinted before, we were just storing all the data in memory, and we were able to do this because we were using Kafka as our input source. If you are not familiar with Kafka, you can think about this as a message queue, but it can remember all the messages that have gone through it. So what our bonus application will do is when it starts up, it will go to Kafka and it will ask for the last 2 months of messages. It will run through them and it will calculate the current state based on those 2 months of messages. Also, because the events themselves, they were timestamped, we will use the timestamp of the events as our clock, as our watch, our clock time on the business logic. If you are familiar with event sourcing, that is basically event sourcing, right? And event sourcing and functional programming at its heart, they share a lot of concepts, because event sourcing and functional programming are pretty similar. So this is how our code, the whole thing, if we put it together, will look like. Then we have a Kafka consumer class where we inject the 2 dependencies that we need, that dependency with all dependencies to create side effects, and then the state. The Kafka consumer will be an active thread. Yeah? So we'll be pulling, using the Kafka pooling API, we'll pull in new events. And for each of the events, what it will do, it's change the state, and that calculates, change the state of the application plus calculate events. And then we'll run all those effects. So that will be basically all the control logic. Now, by using this style, this kind of design, we found some interesting side effects on our code base. The first one is that we will have no getters or setter on our business logic. Right? The second thing was that our business logic was a lot cleaner, because there will be no logs or synchronized blocks on the business logic. There will be no try-catch exceptions in the middle of the business logic, and there will be no logging at all on the business logic. All these concerns will be in another part of the application. So our business logic was a lot cleaner. Now, when we came to unit testing, one of the things that we realized is that we did not use any mocks, because our business logic is a pure business logic, and it just depends on the input parameters, and the output parameters are just plain old Java objects. We can do all of our assertions and we'll test all the logic without having to write any mocks. And because we didn't have any mocks, we also didn't have any useless interfaces. And by useless interface, I mean these interfaces that you have where you have just one production implementation that you usually create because of the mocks. Now to test those side effects on the system, what we actually rely is on a handful of integration or full stack tests. Yeah. This kind of design, it's known as functional core imperative shell. The functional core is what it contains all your pure functions, and you try to there to make as many decisions as possible, and you have no side effects at all. Yeah. And the functional core, in theory, it's supposed to be easier to understand, easier to change, easier to test. And then you have that layer of imperative shell. And that is where you have all the side effects and all that messy code to deal with the real world. And you try to make that imperative shell as thin as possible. And you try to, that imperative shell to have no decision. So you try to avoid any conditionals on that imperative shell. So all the logic should be, or as much as possible, should be in the functional core. Now, because there are other architectures around there that have this circular shape, I want to make something, I want to point something that I think is important. You have a client bonus there in your functional core. That client bonus depends on some interface, and then at runtime, you inject some dependency into that client bonus. That piece of code on the client bonus is not part really of the functional core. That belongs to the imperative shell, because your functional core cannot have any dependency to anything, even in an indirect way, to anything that can perform side effects. Now, this is not good or bad. It's just I want to point out that you don't get all the benefits that you could get if you try to make it pure function. So let's look at the next big difference between Java and Clojure. Clojure is a dynamically typed language, while Java is a statically typed language. This is how will you usually write a Clojure application. So instead of defining classes for your domain, what you will do is just rely on a bunch of maps and lists to represent your business domain. And then your application logic will be just a matter of manipulating that map of lists of strings to get to implement your logic. Now, I don't know what you think about this thing, but for my Java sensibility, this is the exact definition of unmaintainable code. In fact, I find this disgusting. If anybody in my team will go and write that piece of code, I will ask for a very, very, very good explanation about why they are doing that. So for the bonus application, we really decide not to do any dynamic typing and just use the Java type system. Now, when you have been doing Clojure long enough and you come back to Java, your mind starts to, dysfunction. You start to have really weird thoughts. So when you type that class, you start to ask yourself some questions like, what is the value that I get out of this? Yeah? What do I get out of it? And you realize that what you're getting out of this, first thing that you get is I'm going to call it useless to a string. You also get a broken equals and a broken hash code implementation. Now, this is very annoying, but thankfully we have something like Lombok to deal with it. But what are you losing? Suddenly, all the methods, all the code that you have to deal with maps, that inspect maps, to work with maps, suddenly, you cannot use it. In fact, there is nothing in the Java core API, except for the reflection API, that can do anything with this piece of code. In fact, there is nothing in GitHub that you can find that will know what to do with this new class. Yeah. And at this point, you start to understand what Alan Perlis meant with it's better to have 100 functions operating one data structure than 10 functions on 10 data structures. Each new class that we create is actually a new data structure that comes with zero functionality and is completely isolated from any other code. I think this is actually hampering our reusability. But what happens if we just leave that pet object as a plain old data? Well, suddenly you have a reasonable toString, that is the one that you see there on the screen, and you have equals and hash code, proper one, that you get it completely for free. But also, you can reuse all the functions, all the methods, all the libraries that you have that can work with maps and lists and everything, right? The Clojure community has embraced this idea of representing as many things as possible as plain old data. So for example, who can tell me what is this? Who can guess it? I'm looking at the chat. Come on, one guess, at least one guess. Not always go for one guess. That's right, that's an HTTP request, right? You can guess it. You don't need to look at a lot of APIs. This is an HTTP request. So an HTTP server, what it needs to do, it gets this map, plain old map, as an input parameter, and using the same API that used to build your business logic, just need to transform that map into another output map. So this is an HTTP response. And you can do this thing with a lot of things. For example, your SQL queries, or your database result sets, or this can be also a CSV file, or this can also be a table. You can do it with HTML and CSS. You can do it with your configuration. And in fact, you can do it also with data about your data, with your metadata. So when you embrace this idea of everything as plain old data, suddenly you are using the same API to build your business logic, your infrastructure code, to manipulate your configuration, and to work with your metadata. Okay, so you just have one API that you keep reusing all over. So that dynamic typing in Clojure, I have to say that after learning it, is not as bad as I expected. Now, types is just one of the difference between dynamic and static in Java. Clojure provides this kind of dynamic development environment. I want you to imagine that you need to add a new piece of functionality in whatever project you're working right now. The way you do that in Clojure is that the very first thing that you do before writing any code, you start the application. And once the application has started, then you start modifying the application, the running application, to build the functionality that you want on the running application. And you can do this thanks to a REPL. I know that in Java now we have a REPL, but it's not exactly the same as a Clojure REPL. With a proper REPL, you never have to redeploy or restart or rebuild or repackage your application. You just start your application, connect to it, and then one bit at a time, you change that living, that running application without any delays. With a proper REPL, you get like the same feeling, the same ergonomics as a Unix shell. A proper REPL is like having a debugger attached to JVM all the time. It's like having the Google Dev Chrome tools, the Chrome Dev tools, but having them within your IDE and on the JVM. And if you're doing TDD, a REPL actually improves that TDD workflow. This is a weird subject. So I have a whole talk there about what a REPL actually gives you. And I have to say that the REPL is the thing that I miss the most when I have to do any Java development, because it gives you a really, really fast feedback loop that, you know, not even TDD can give you. And the last section of the talk. Obviously, we decided not to use the Clojure syntax, because if not, I wouldn't be giving this talk. But for all of you that, you know, run screaming whenever you see a piece of Lisp, I have some good news for you. First thing, that in Clojure, the same as most modern JVM languages, semicolons are optional, right? And we all know that that's a huge improvement over Java. In fact, with, you know, this feature is so awesome, and it's such a big productivity boost that Clojure goes one step further. And in Clojure, commas are also optional. Just think about those millions of commands that you have to type. Yeah? How much time you will save if you didn't have to do that. Now what you're thinking, right, is like, oh, what about all those pesky parentheses that Lisp are so infamous for? So even here, I have a good news for you. Those are two pieces of code from one of my teams. when we were learning Apache Spark, we happened to build the same application, but we did one in Clojure, one in Java. Yeah, basically the same application. And that's the core logic of the application. Now, there is one big difference between the two. Let's count the number of parentheses. The Java version has 16 parentheses, while the Clojure version has 10 parentheses. So by writing Clojure, you are going to write 40% less parentheses than in Java. But not only that, for this particular application that have exactly the same functionality, we found out that the Clojure code base was 1/10 of the code of the Java application. 1/10. Just imagine if in your project that you're working right now, you could throw away 90% of your code. Wouldn't that make your life a lot easier? But enough of silly jokes about this. I'm going to try to explain why Lisp people love their parentheses so much. And for that, we are going to see another piece of Clojure code. So when you write a Clojure application, this is basically what you are doing. Here, we are defining a new function called +1 that accepts 2 parameters, A and B, and it returns a map with the time of the computation and the result of adding A, B, and 1. Yeah. Obviously, this is not how you write Clojure, but this is basically what you are doing. And if you look at it, it's like, what is this? This is just plain old data. When Lisp people say that code is data, this is what they mean. It's just data. Because it's data, you can use exactly the same API that you use for your business logic and your infrastructure code. You can use exactly the same API to inspect, manipulate, generate the code. So metaprogramming in Clojure, so writing programs that write programs, it's just a matter of using the same API to change a piece of data. And I think this is why Lisp people love their parentheses so much, because it makes metaprogramming extremely easy. So that's all that I have. So in summary, try to write as many pure functions as possible. Yeah, because they make your life easier. And you do that by trying to separate state management from business logic and try to separate the decision of which effects to make from executing the effect themselves. After using Clojure, I'm not so sure that, I think there's a good trade-off between static and dynamic typing. And it's true that in Clojure, you will miss, your refactorings, your Java refactorings, those are amazing. And it's true that you will sometimes just spend or waste a lot, some time just chasing some typo, but everything as data brings a different perspective on that dynamic typing. Now that dynamic development environment, that's something that, oh my God, I couldn't live without it right now. It's just like, it's so awesome, that feedback loop that's like, you need to experiment. And last, please don't be really scared of the parentheses. The same way that you will never even dream to write a Java application without the support of an IDE, the same is true for Clojure. And the IDE will take care of all those parentheses. And in a couple of months, you will not see those parentheses anymore. And they come, they bring a lot of power. And I want to finish with a quote from another quote from Alan Paris. A language that doesn't affect the way that you think about programming is not worth knowing. Clojure has been, for me, one of those languages, immutability by default, Lisp syntax, macros, functional programming, the REPL. There has been big lessons that have changed the way I approach programming, that they have changed the way that I design applications. Now, none of this is really Clojure's most important lesson. The biggest lesson that I have by learning Clojure has been how blind I was, how close-minded I was to other ideas, other things, because they look disgusting, because they don't look familiar. Yeah. Any of you have asked me a few years ago to go and learn a dynamic type Lisp? I would say like, well, don't waste my time. And here I am talking about it. So I want to encourage everybody that this year to go and learn a new language. And it doesn't need to be Clojure. Just pick anything, but pick something that is really different to what you are used to. And I'm sure that in that journey, you will learn something that you will bring back to your day-to-day work as a Java developer. And in the worst case, it will just make you weirder and harder to relate to. Thank you very much for your time. Are there any questions?
Yeah, thank you very much, Daniel, for your great talk. As you mentioned, we now have some minutes for questions. Looking at the chat.
I don't see any questions, but I want to ask for one more thing. Yeah. Oh my gosh, what? I want everybody to focus on that point for 1 second. Yeah. Really focus, really pay attention. If you didn't pay attention to any of the other stuff and you were working or whatever, I'm happy. I just need you to now pay attention to that point. Yeah. Everybody ready? I'm going to assume that you are. This doesn't convince you to try Clojure, I don't know what will.
Convince us, of course, to use Clojure and to ask a question in the chat, because there's one.
Do you really think it's a good idea to keep everything as a map of strings? I have worked on a few systems written like that, and they are incredibly difficult for anyone except for the people who wrote it to understand it. It's not something that I will advocate doing. I found clearly defined objects are much easier to debug and understand. Yeah, so this, oops. Oh, sorry, are we back? Yeah, sorry, are we still?
Stay on.
Okay, correct, sorry. So it's true, yeah, that at the beginning looks scary, and this is Clojure is not the first. I did JavaScript a long time ago, and my experience with Clojure versus JavaScript dynamic typing, it's a completely different world. I cannot explain why, but they are not the strings. So the first thing is that you don't use the strings in Clojure. What you use is something called keywords, and keywords are actually easier to find and to search for, and to make sure that you are using the right thing. So keyword, I don't know how to explain this, but it's like a nicer string, like a constant, right? It will be like constant. In our case, will I use it in Java? Like, no way. If I'm using Java, as I explained, I will not use it. But for some reason in Clojure, it's just maybe just a natural thing to do. So use strings all over the place. No, it's just, I think the language has to make it idiomatic and make it easy to work with. So the Clojure API, it's very good at actually we're working with maps of keywords with you know, strings. So yeah. So always no. Sometimes, I think so, yes.
Okay, I think we are coming to the end of this session. Thank you very much again, Daniel, for these insights. We are now convinced Lisp and other users, of course, don't need Java anymore, or what would you say? No.
Yeah, if anybody has any question, I will be online, or just ping me on social media, whatever it is. Yeah. Thank you very much for your time.
We'll use the chat here for questions. And yeah, thank you, Daniel. Thank you for watching us. And yeah, we are heading to the next session. Have fun at the conference. Bye-bye.